Hello, it's Ryan. Today we'll be talking about collisions, but really we'll be discussing momentum and the principle of conservation of linear momentum. But we need to start by defining collisions for you. Collisions, or a collision, is an event that involves two or more bodies that interact via forces. So we'll write that. A collision is an event that involves two or more bodies that interact via force. So really, any time that two or more bodies interact with one another with some sort of force, then we would say that those bodies are colliding with each other. And when we talk about collisions, we get a little bit more in depth by breaking them into three different types of collisions. And so we'll define for you the different types of collisions. The first is an elastic collision. And an elastic collision is kind of like a perfect collision. And for each of these three types of collisions, what I'm really going to do is I'm going to tell you the conditions that must hold if this type of collision is the collision we're looking at. So there's going to be three conditions. The first is that momentum is conserved. And I'll define momentum for you soon. Momentum is conserved. The second is that kinetic energy is conserved, which we usually call KE. Kinetic energy is conserved. And lastly, we like to note that no permanent deformation occurs. No permanent deformations. No permanent deformation occurs. So those are the conditions if we're talking about an elastic collision. The next type of collision is an inelastic collision. And once we talk a little bit more about each of these, I think that the bullets will make more sense. I just like to get all your notes down and then we can discuss it. So momentum is conserved. I'm going to start writing momentum like this, and when I define it, that'll make more sense. Momentum is conserved. Kinetic energy is not conserved. And I'm not saying that energy is not conserved. I would never say that, but I am saying specifically that the kinetic energy in the collision is not conserved. And finally, permanent deformation occurs. So the bodies involved in the collision will be permanently deformed from that collision. The final type of collision is really a subset of inelastic collisions, but I like to create a whole new category for it. It's perfectly inelastic collisions. And this will have one final or extra bullet. So momentum is conserved, of course, in every collision. As you can see now, momentum is conserved. Kinetic energy is not conserved. Permanent deformation occurs, for sure. And lastly, in a perfectly inelastic collisions, the bodies stick together. Stick or start, I'm going to note, together. So that's the fourth special condition to create a perfectly inelastic collision. Otherwise, it's just an inelastic collision all the same. I would like to just add a brief note here. We'll note the work energy theorem. So remember, the work energy theorem was work is the change in kinetic energy. But remember, the weak form was really the change in total energy, wasn't it? So we know that the work done on any body in a collision is going to equal the change in energy. And we know POCO, the principle of conservation of energy. And so if you were to read these definitions and we say kinetic energy is not conserved, then you might be wondering, where does the KE go? And so the answer is that it goes into this permanent deformation that happens to the bodies. If you think of a car accident, you can imagine the permanent deformation that occurs to the cars and hopefully no one else. So it takes a lot of energy, but ultimately that really is turned into thermal energy. So the energy that appears to be lost, just like we talked about in other videos, it gets converted to thermal energy. So I just wanted to make that note to remind everyone that our energy doesn't really go away. When we say kinetic energy is not conserved, it really is conserved. It just isn't turned into kinetic energy. It's turned into something that we won't really be able to use anymore, namely thermal energy. So just briefly, we'll give some examples of each type of collision. So normally I would have you all come up with these examples with me, but for elastic collisions, so we might want to note here that elastic collisions, they don't necessarily really exist in the real world. The closest thing that we think come to elastic collisions might be atomic collisions, collisions between atoms. We approximate those to be elastic collisions, but even atoms probably warm up. Another approximate elastic collision might be a superball if it's a really nice superball, but that's iffy. Superballs definitely become permanently deformed. When we have pool balls collide, or billiard balls if you don't like pool balls, when we have billiard balls collide, those are often approximated at as elastic collisions. And finally, another one that can sometimes be approximated as elastic might be bumper cars. You know, bumper cars at fairs, but they have to be under 5 miles per hour. So less than 5 miles per hour. Otherwise, you get a lot of permanent deformation in those bumpers. You might not see all of the deformation. It might not be visible to your eye, but it definitely will be there. For inelastic collisions, typical car accidents, as long as the cars don't stick together, tennis, like a bouncing tennis ball, baseball hitting a bat, so I'll put baseball bat, and I'll just put etc. Those are some examples. And perfectly inelastic collisions, remember, this means that the bodies have to either start together and then separate during the collision, or come together during the collision and stick together after the collision. And so something might be a baseball being caught. If you catch a baseball, that means the ball collided with your hand and you caught it. You could note then also being thrown, or thrown, because you start as one body, and then when you let go of the ball, you're now two bodies. So it's like the reverse of catching something. If you drop something on the floor and it sticks to the floor, so we'll say dropping Jello on the floor. I don't know, etc. Anytime two things stick together. If a car collision occurs and the cars stick together after the collision, then that would be considered a perfectly inelastic collision. So those are the examples, some examples of the three different types of collisions that I've outlined. So now let's get some definitions. So some definitions for you. I think we should probably start by defining momentum. Momentum. And I think maybe we could say that any moving body has momentum. Momentum mathematically is a vector quantity, and it's usually given a lowercase p with a vector symbol, and it's equal to mass times velocity. So we can say where p is momentum, m is mass, and v is velocity. That is momentum. And so if you can tell, momentum is actually kind of a simpler equation than most. So working with it might not be as mathematically as complicated as some other problems. Anytime we're working with a collision or working with momentum, the same condition always holds, and that's that momentum is conserved. And so we're going to talk about that. The next conservation law in our class is the principle of conservation of linear momentum. What do you think we'll call it? The principle of conservation of linear momentum, or what we'll often refer to as POCOM. And POCOM is just like the principle of conservation of energy, whereas it's defining a new quantity that is always conserved. And so we'll say in a closed system, I don't like that. We'll just say for any collision. Let's not make it more complicated than it has to be. In any collision, because by definition that will be between two or more bodies. In any collision, momentum is conserved. And so that's kind of an obvious definition. What we're really interested in for our class is probably the mathematical definition. It's very much like POCO. We'll just always use the same sort of process here. Mathematically, we will compare the total momentum before a collision to the total momentum after a collision. So technically, what this tells us is that momentum before a collision is always equal to the momentum after a collision. Oftentimes, what a book will write is that the change in momentum for any collision is equal to 0. But we will use this, and then you might note to yourself that before is and after we'll analyze all the bodies separate from each other, meaning we'll add all their momenta together separately. But that's it. And once we do examples, I think it will all be clear. Something interesting about momentum is that originally we thought momentum was a fundamental quantity. Remember way back when we talked about fundamental quantities of motion, velocity was one of our fundamental quantities that described motion or a change in position with respect to time. We originally thought that that was momentum. Even when Isaac Newton came along and created his second law, the way he really introduced his second law was like this. Now that's not the notation he used. He would have used p dot like that, but it's the time derivative of momentum. And so for our class, the average force would be equal to the change in momentum over the change in time. So that's really how Newton introduced his law in a sense. He talked about the changing momentum with respect to time being proportional to the force or equal to the force. So if we were to play around a little, let's play around a little with this equation. We could derive the next fundamental equation from this chapter, and really the last one. It's impulse. But if we were to break delta P up, so we have F average equals delta mv over delta t. I'm going to put the delta on the v because mass is usually constant, unless you're doing rocket science. And we're going to multiply delta t over, so we'll do F average times delta t equals m delta v. And this is a very special equality here. This is called impulse. So I'll rewrite it for you. Impulse is usually written this way. F delta t, and we're doing an average. Impulse is usually, it can be done with a derivative, which you would end up with differentials and integrating, but is equal to delta p. That's the impulse equation, and it's worth noting that both sides of this equation are equal to impulse. So both sides represent impulse. Impulse is another quantity that we analyze when we're dealing with collisions. And this actually has a lot of real-world applications. What this is saying in English, this equation, it's saying that the change in momentum, which is equal to impulse, the change in momentum during any collision is the same as if you knew the force that causes the change in momentum multiplied by the time that the collision is taking place. And this whole quantity is also impulse. I don't think that that helps, but let's put it into a perspective that unfortunately everybody understands. So inevitably in life, you've either witnessed or been a part of some sort of car accident, right? Now, if you remember way back in the 50s, who are we kidding? You don't remember that. But if you did, or if you look it up, we used to make cars very differently. Cars used to have steel dashboards, steel steering wheels, things that didn't have a lot of forgiveness if your head ran into them at 40 or 50 miles an hour. It would cause serious issues, especially for your brain. The other thing that cars were lacking back then were safety belts. That's right, and airbags. Anything for precaution, it just was not there yet. We didn't understand the danger. So in the 50s Cadillac, you may look really good, but if you were to get into a car accident and your body was going 45 miles an hour inside the car that you're driving, so here's your car going 45 miles an hour, and maybe, unfortunately, you end up finding a tree. When your car collides with the tree, this would be a perfectly inelastic collision because you aren't moving, and I'm sure that the tree isn't moving either. Your velocity goes to 0, and so your change in momentum would be mass of you in your car. I guess we're talking about you, so mass of you, V final minus V initial, and V final is 0. And so you get a very large change in momentum for your body. When we talk about impulse, that change in momentum is kind of constant for something like this car accident. And so what we would want to do is we would want to alter the time that your body has that change in momentum. We would want to increase the time that your body slows down, and in turn we would be decreasing the force that causes your body to slow down. So let me back up. As you're driving, if you do somehow end up hitting this tree and it's the 50s, there's nothing, no airbag, no seatbelt to stop you. Your body is going to collide with the nearest object, either the steering wheel, which was made of steel, or the windshield, which you probably fly right through. And your interaction time with that object, if you hit the steering wheel and it's made of steel, the time you interact with that steering wheel will be very, very small. That means the force that causes your body to stop will be very, very big. And that's what causes serious damage. And that's why we came out with safety belts and airbags, and we put that nice rubber material or leather on your steering wheel, and we make your dashboard out of that nice rubber material. It's all in hopes to elongate the time that you collide with something in the event of an unfortunate accident, and by elongating that time, we would be decreasing the force that was on your body causing the change in momentum. Point of all this is our final topic, or our final equation we'll be using when we deal with collisions, is momentum, where you can determine things like the impulse force or the impulse of a collision. So, from our new material, we have types of collisions that you can identify if you are given some sort of collision in a problem. If you are given any sort of collision ever, you know that momentum is conserved, and you'll have to apply the principle of conservation of linear momentum. And depending on the collision, you may also get to use kinetic energy, but that's for one type. So we have momentum, a new quantity, the conservation of momentum to work with it, and then finally impulse. Stay tuned for some examples.